Hey folks, this is the first of 4 videos on correlation. This particular unit of the course, we're really only going to cover correlation and regression, so both lectures will be a little bit lengthier than a normal one-topic lecture, but they should be thorough to get you fully covered and ready to calculate a full correlation or regression and understand the use of that particular statistic. Okay, so to do so, we're going to start out by introducing something that's sort of related called a standardized or z-score. So what are we going to talk about over the course of this lecture? Well, standardized scores, obviously, because I already said that we were going to do that. We'll talk about correlations, obviously. I said we were going to do that. We'll describe the characteristics of them, the relationship or lack thereof to the causal or cause and effect relationships that we try and find with experiments. We'll talk about the use of a technique called partial correlation. And then I'll talk about a field of opportunity, if you will, right? An area that you might want to go into for employment called psychometrics. So if you find yourself good at statistics, psychometrics is a highly lucrative field looking at psychological data, I guess to highly summarize. And then we'll talk about how correlation can be used to assess reliability and validity of various psychological instruments that we create. Okay, so let's start by talking about standardized scores. Correlation is all about comparing two variables and seeing how they're related. Well, standardized scores is really about that too. Standardized scores allows you to take a variable, no matter what that variable is, and transform it into what's called a standardized score, and now you can compare it to this, to this, to this, to this, to this, and to all these different increments. So, for example, let's say I decide I want to figure out what the average cockroach size is on various continents, right? So I grew up in Florida. There are big cockroaches down there in Miami. I'll tell you, they are huge. That's when I became curious about this. So I call researchers all around the world, and I say, can you tell me on average how much a cockroach weighs in Australia? Can you tell me how much a cockroach weighs in Canada? Let's see. In different countries, different continents, all around the world. And so I call and I get some information back, right? And so here's 3 examples of some information I could have gotten. One person tells me they weigh 14.17 grams here. Excuse me, another person, 8 drachms. I'm jumping ahead here. One person says they weigh 8 drachms. Another says they weigh a quarter of a pound. Another says 98 grams. Those are 3 different scales, 3 different variables. Now, because they all measure weight, we can figure out how to convert from drachms to pounds to grams and put them all on the same playing field. So we can say that a 14.17 gram cockroach is the 8 drachms. So a quarter of a pound cockroach, that's a fucking big cockroach, is 113.4 grams. And then 98 grams. So now they're all on the same scale. So it's easy to be compared. But how would you do that if they were completely different things, like the number of siblings that you have and my temperature? They're probably not related, but how could I even put them on the same scale to compare them? Is my temperature higher than normal? And is its higher or lower than normalness, like the degree to which it is higher or lower than normal? Is that the same to which my number of siblings is higher or lower than the normal or average? We need some way of putting them on the same scale to be able to compare them, and that's what standardized scores are for. You take completely different variables, often different scales, and you standardize them. Standardized scores are what are called z-scores, so it's a lowercase z, and just like all our statistics and parameters, we italicize them when we type them. And essentially, instead of now creating a distribution that says where you are on that scale relative to other people on the scale, now we say where you are in standard deviation units relative to everyone else in that population. So am I 2 standard deviations above the mean? Am I 2 standard deviations below the mean? My raw score already sits somewhere in that larger distribution. Maybe I'm way above the mean, maybe I'm way below the mean. All I'm doing is converting that distribution of raw scores to a distribution of scores that simply represent how far each one is from that mean. Why is that useful? Because you can do that now with any variable. They could be temperature. I find out the average temperature is 85, standard deviation is 15. I happen to be at 100. Well, I'm 1 standard deviation above the mean. That means I'm 1 z-score, right? My z-score of 1 for that raw score of 100. So I'll show you all that conversion stuff here in a second, but that's really the value of the z-score. Then you can take all those z-scores, just like you can take raw scores, and you put them in a giant distribution right? Big, giant, normal distribution, because about half the scores are going to fall above the mean, half the scores are going to fall below the mean, right? That's just roughly how those distributions are going to shake out. And because it's a normal distribution, we know the shape of it so well that we can now say your percentile as a function of your z-score. So if you said I was at a z-score of 2, well, I could use this table here, and I'll teach you how to use this table as we move along, to look up the z-score of 2.0. And in this particular case, z-score of 2.0 corresponds to a number on the table of 0.477, so I'll round up to 4.8. Okay? If I take that 4.8, what it's saying is that black portion of the table is 48% of the population. So my z-score sits above 48% of the population, and that's just the 48% that's above the mean. The other 50% below the mean are over here, so 50 plus that, I'm well above a huge section of that population. And z-scores, because they're in standard deviation units, tell you precisely where your score is relative to that mean. Is it above it? Is it below it? And by how much? So one thing to note then is that distribution of z-scores, because it represents scores that are above or below the mean, the center point of that distribution is not going to be above the mean or below the mean. So its z-score is always going to be 0. Right? And the standard deviation then is going to be 1 of this distribution. That's always going to be the case, because this is a distribution not of raw scores, but of standardized scores, z-scores that represent whether you're above the mean or below the mean. Right? Half the score is above and below in a non-skewed normal distribution. And so z-scores are always going to have a center point of that distribution of 0. Again, this means we can take a raw score, right? Say I scored an 85 on a test. I know the mean to be a 70. I know the standard deviation to be 10, right? So if I know that information, the average on the test was a 70, standard deviation was a 10, I scored an 85, well, I can quickly figure out then that because I'm 15 points above the mean and standard deviation is 10, I'm 1.5 standard deviations above the mean. And then using that table I showed you, I go right back over there and look up then what percentage of the distribution falls below my score, what falls above my score. And using that information, when we get to inferential statistics, is where we start to say, what percentage of cases would really fall beyond that difference between the control group and the experimental group? In other words, did our independent variable produce a large enough difference that it's well beyond what we would see due to chance, and is instead way in one of these extreme ends of the tails of these distributions? So a little bit of a preview, but that's where we're going to go using this sorts of information. So how do you create the z-score, right? I talked a lot about it. It's a very, very simple formula. Z is equal to the raw score x, right? Whatever the raw score is, your score is their score, whatever score it is you're looking up the z-score for, minus the mean of the population divided by the standard deviation of the population. So we've done means, we've done standard deviations. It's really easy. You just plug in the mean of the population, the mean of the standard deviation, and then whatever raw score you're trying to calculate a z-score for. Right? And you can do it for every raw score. Every one will have a place somewhere in the distribution represented by how many standard deviations it is above or below. Okay, so super easy. Let's see an example for how you might use something like this. Okay, but first, actually, let's watch a quick video that describes a little bit about this process.
In this video, we'll be learning about z-scores and standardization. By learning about both of these topics, you will learn how to calculate exact proportions using the standard normal distribution. What is the standard normal distribution? The standard normal distribution is a special type of normal distribution that has a mean of 0 and a standard deviation of 1. Because of this, the standard normal distribution is always centered at 0 and has intervals that increase by 1. Each number on the horizontal axis corresponds to a z-score. A z-score tells us how many standard deviations an observation is from the mean mu. For example, a z-score of -2 tells me that I am 2 standard deviations to the left of the mean, and a z-score of 1.5 tells me that I am 1.5 standard deviations to the right of the mean. Most importantly, a z-score allows us to calculate how much area that specific z-score is associated with, and we can find out that exact area using something called a z-score table, also known as the standard normal table. This table tells us the total amount of area contained to the left side of any value of z. For this table, the top row and the first column correspond to z values, and all the numbers in the middle correspond to areas. For example, according to the table, a z-score of negative 1.95 has an area of 0.0256 to the left of it. To say this in a more formal manner, we can say that the proportion of z less than negative 1.95 is equal to 0.0256. We can also use the standard normal table to determine the area to the right of any z value. All we have to do is take 1 minus the area that corresponds to that z value. For example, to determine the area to the right of a z-score of 0.57, all we have to do is find the area that corresponds to this z value and then subtract it from 1. According to the table, the z-score of 0.57 has an area of 0.7157 to the left of it. So 1 minus 0.7157 gives us an area of 0.2843, and that is our answer. The reason why we can do this is because we have to remember that the normal distribution is a density curve, and it always has a total area equal to 1 or 100%. You can also use the z-score table to do a reverse lookup, which means you can use the table to see what z-score is associated with a specific area. So if I wanted to know what value of z corresponds to an area of 0.8461 to the left of it, all we have to do is find 0.8461 on the table and see what value of z it corresponds to. We see that it corresponds to a z value of 1.02. The special thing about the standard normal distribution is that any type of normal distribution can be transformed into it. In other words, any normal distribution with any value of mu and sigma can be transformed into the standard normal distribution where you have a mu of 0 and a standard deviation of 1. This conversion process is called standardization. The benefit of standardization is that it allows us to use the z-score table to calculate exact areas for any given normally distributed population with any value of mu or sigma. Standardization involves using this formula. This formula says that the z-score is equal to an observation x minus the population mean mu divided by the population standard deviation sigma. So suppose that we gathered data from last year's final chemistry exam and found that it followed a normal distribution with a mean of 60 and a standard deviation of 10. If we were to draw this normal distribution, we would have 60 located at the center of the distribution because it is the value of the mean, and each interval would increase by 10 since that is the value of the standard deviation. To convert this distribution to the standard normal distribution, we will use the formula. The value of mu is equal to 60 and the value of sigma is equal to 10. We can then take each value of x and plug it into the equation. If I plug in 60, I will get a value of 0. If I plug in 50, I will get a value of negative 1. If I plug in 40, I will get a value of negative 2. If we do this for each value, you can see that we end up with the same values as a standard normal distribution. When doing this conversion process, the mean of the normal distribution will always be converted to 0, and the standard deviation will always correspond to a value of 1. It's important to remember that this will happen with any normal distribution no matter what value the mu and sigma are. Now, if I asked you what proportion of students scored less than 49 on the exam, it is this area that we are interested in. However, the proportion of x less than 49 is unknown until we use the standardization formula. After plugging in 49 into this formula, we end up with a value of negative 1.1. As a result, we will be looking for the proportion of z less than negative 1.1. And finally, we can use the z-score table to determine how much area is associated with this z-score. According to the table, there's an area of 0.1357 to the left of this z value. This means that the proportion of z less than negative 1.1 is 0.1357. This value is in fact the same proportion of individuals that scored less than 49 on the exam. As a result, this is the answer. Let's do one more example. When measuring the heights of all students at a local university, it was found that it was normally distributed with a mean height of 5.5 feet and a standard deviation of 0.5 feet. What proportion of students are between 5.81 feet and 6.3 feet tall? Before we solve this question, it's always a good habit to first write down important information. So we have a mu of 5.5 feet and a sigma of 0.5 feet. We are also looking for the proportion of individuals between 5.81 feet and 6.3 feet tall. This corresponds to this highlighted area. To determine this area, we need to standardize the distribution, so we will use the standardization formula. Plugging in 5.81 to this formula gives us a z-score of 0.62, and plugging in 6.3 into the formula gives us a z-score of 1.6. According to the standard normal table, The z-score of 0.62 corresponds to an area of 0.7324, and the z-score of 1.6 corresponds to an area of 0.9452. To find the proportion of values between 0.62 and 1.6, we must subtract the smaller area from the bigger area. So 0.9452 minus 0.7324 gives us 0.2128. As a result, the proportion of students between 5.81 feet and 6.3 feet tall is 0.2128. If you found this video helpful, consider supporting us on Patreon to help us make more videos. You can also visit our website at simplelearningpro.com to get access to many study guides and practice questions. Thanks for watching!
Okay, now let's do this example real quick. So we've got Anna, we've got Donna. Okay, Anna has just taken the ACT because she wants to apply to college. Great job, Anna. She scored 28 out of a possible, that should say 36. If she scored 28 out of 26, then Anna's a badass here, but that's a 28 out of a 36, excuse the typo. Donna has just taken the SAT to apply to college. They took different exams. She scored a 1,430 out of a possible 1,600. So they're way different scales. The ACT is out of 36. The SAT is out of 1,600. Who did better? Who's the stronger applicant? If a college had one spot and they had to pick Donna or Anna, who scored better? They took different exams. We can use standardized scores to figure this out. Who is farther above the average than the other one, right? Are they different, in fact? So let's take Anna first. She got a 28 out of a possible 36. Now, I've looked it up. The national average, so the mean, mu, for 2018 to 2020 was 20.7. So she's above the average. That's great. She's a full 7.3 points above the average. Standard deviation for those years was 5.9. So we have the information we need, right? Our formula requires that we know population mean and population standard deviation. So now we can plug in her raw score in the place of x, and we see 28 minus 20.7 divided by 5.9. We end up with a z-score of 1.24. So Anna is 1 1/4 standard deviations above the average. Now let's look at Donna. Donna got 1,430 out of a possible 1,600. The national average for 2017 to 2020, I also looked up, was 1,060. So she's, again, just like Anna, considerably above the average. The standard deviation for those years was 195. So we'll do the same thing. We'll take that mean and standard deviation. We're going to plug it into our formula along with Donna's 1,430 score. And we're going to calculate the z-score then for Donna. Donna has a z-score of 1.9. So if Anna's z-score of 1.24, we can look that actually up on the table here. So we can see over on the left, that first column, those are the first parts of the z-score, so we can look up the 1.2 and go all the way down to where the 1.2 is, and then across those columns, instead of those rows, we can look for the last digit, the 4. So if we sort of connect up where those are, right, where the 1.2 is, where the 0.04 is, and then we meet them in the middle, we see that that percentage is a 0.3925, okay? 0.3925 added to the 50% that's on the other side of the distribution would tell us that Anna's percentile is 0.8925, or the 89th percentile, meaning 11% of the population scored higher than her, but 89% of the population scored at or below her. So pretty good. Congratulations, Anna. Let's do the same for Donna and see what her z-score means. So Donna, remember, got a 1.9 z-score. So we're going to look at the table again. Now hers is all the way down there at the bottom. 1.9. There's nothing in that last decimal place, just a 0. So we line up in that first column. We see the connection is a 0.47, right? 0.4713 to be specific. So let's look at this a little bit closer. We put the 0.47 here, add the 50% that's on the other side of the table, and Donna actually is in the 97th percentile. So while Anna did fantastically being in the 89th percentile, Donna's 97th percentile makes her the more impressive student. And that is one good way of using z-scores, to learn more about where that raw score sits in that larger distribution, right? Finding out where you are relative to other scores can oftentimes be far more informative than simply knowing your raw score. All right, so that's it for this one. When we start back, we'll talk about correlation, and then we'll get into a big calculation on correlation, and then I'll tell you some of the ways we can use correlations for things like reliability and validity. All right, cheers.